Consider these clips from popular movies. For every clip, the focus is on the same scene and the same people, but there are abrupt changes in the camera viewpoint. This is what we call a shot change. Shot changes are very common in edited media like movies and TV series, and they are often treated as discontinuities that lead to independent processing of each shot. However, individual shots include only partial information about the scene. In the case of humans, for example, if we treat each shot independently, we have to deal with challenging viewpoints and truncated bodies. Recent approaches for 3D human reconstruction perform well when most of the body is visible, but struggle in cases with heavy truncation. However, it is the shots or viewpoints that are discontinuous, not the underlying scene in and of itself. In fact, we know that the 3D pose should change smoothly across each sequence. This means that each shot provides different viewpoints of the same 3D scene, and each viewpoint can be treated as complementary information for the reconstruction. Effectively, we can integrate information from otherwise independent shots, which allows us to improve the overall quality of the 3D reconstruction. To achieve this, we propose a multi-shot optimization method that allows us to reconstruct humans across shot changes. This multi-shot reasoning can be applied on general movie sequences and can greatly improve upon failure cases of previous single or multi-frame approaches. We can easily scale up this procedure to large-scale movie datasets, like AVA, and reconstruct many hours of 3D human sequences. We refer to this dataset as MS-AVA for multi-shot AVA. At the core of our framework, we introduce a multi-shot optimization approach to build offline a large dataset of 3D human sequences for movies. This data can be treated as pseudo-ground truth to train direct prediction models for human mesh recovery, both from a single image and from video. For our multi-shot optimization, we follow the Simplify setup that fits the simple model to 2D joint detections using a set of priors. Furthermore, we additionally want the underlying 3D mesh to be consistent. However, since the camera viewpoint can change abruptly, we cannot enforce smoothness constraints on the camera frame. Instead, our formulation decomposes the global orientation of the body model from the body pose and applies the smoothness term on the canonical frame. This can enforce continuity of the body pose across the shot boundary, while also recovering the camera viewpoints for the different frames. Note that recovering the camera locations using traditional SFM methods would be very hard because of the wide baseline of the different shots and the minimal overlap of the camera views. In our approach, viewpoint recovery is feasible exactly because humans are treated as anchors in the scene. We run our multi-shot optimization offline on the large-scale AVA dataset, and we recover many long sequences that can span multiple shots. The result of this procedure is our new MS-AVA dataset. The big advantage of MS-AVA is that it includes many diverse and long tracklets, unlike previous datasets. This is highlighted also in the figure on the right, where we plot the raw duration of all tracklets that last for more than 20 seconds on standard benchmarks. After reconstructing MS-AVA, the second step is to demonstrate how the plethora of collected data can be beneficial to training of computational models for human mesh recovery for both single image and video inputs. In the single frame case, we include this data in the training of the HMR model. Given that MS-AVA includes a lot of truncated views of the human body, the trained model is significantly more robust in the case of truncations at test time. For the video setting, we propose a model for human mesh and motion recovery, where the temporal encoder is based on the transformer architecture. We call this THMMR. A benefit of the transformer is that we can easily control attention and ignore shots of a different individual. This is very common in movies where an identity can change between shots, and traditional recurrent and convolutional models do not have a principled way to deal with this type of missing data. Next, we demonstrate qualitative results of our approach. Our multi-shot optimization uses the shot continuity and relies on the information provided in more than one shot to improve the reconstruction. Our single-frame model outperformed previous models in the very challenging partial humans dataset. We perform extensive experiments for our framework on our MS-AVA and the standard benchmarks. We present many reconstructions for our robust HMR model. Finally, we provide temporal reconstructions for our T-HMMR model on AVA. And compare the transformer encoder with recurrent and convolutional architectures for the temporal encoding. We have highlighted the common modes of failure in cases with missing input frames and shot changes. Thank you for watching.